A silent ship must burn for 1,000 years to reach another star. The dream of centuries-long space travel depends entirely on one thing: the energy systems capable of powering starships. This is not about bigger fuel tanks, but about reimagining power itself, from harnessing miniature stars to capturing the ghostly energy of empty space. By the end of this exploration, you will understand the radical physics that could turn humanity into an interstellar species. We will confront the reality of black hole engines and ask if we can truly siphon power from the fabric of the universe. What does it reveal about our ambition when we design machines meant to outlive civilizations? The numbers alone are enough to silence any room. Voyager 1, that tiny messenger carrying a golden record, is hurtling away from us at over 38,000 miles per hour. At that incredible speed, a pace that could circle our planet in under an hour, it would still require more than 70,000 years to reach the doorstep of our nearest stellar neighbor, Proxima Centauri. That timescale is not just long, it is incomprehensible. It is a span that sees ice ages come and go, that watches continents drift and civilizations rise and fall into dust. A ship embarking on such a journey cannot be a vessel that merely coasts. It must be a world. It must generate its own light, its own heat, its own air, and crucially, its own relentless push forward for centuries without pause. The fundamental challenge, therefore, is not distance but time powered by energy. Chemical rockets, the fiery workhorses that lifted us from Earth, are useless here. They are spectacularly inefficient, requiring immense weight in fuel for a relatively tiny amount of thrust. To propel a starship for even a fraction of the necessary duration with chemical propellants would demand a fuel tank larger than a planet. So we must discard the very idea of carrying all our energy with us at the start. The solution lies not in a stockpile, but in a source, a system that can create or collect more energy than it consumes across lifetimes. This forces a leap in our thinking, from engineering bigger containers to mastering the physics of the universe itself as a power supply. To cross the ocean between stars, we must learn to build engines that can drink from the void. The universe does not negotiate with ambition. It presents a ledger, and the first entry is a brutal equation named for Konstantin Tsiolkovsky. This is not a suggestion. It is a law of motion as unforgiving as gravity itself. To understand why our familiar rockets fail among the stars, you must first understand this simple, devastating math. The rocket equation states that every bit of speed you want to add requires you to burn propellant. But that propellant has mass, and that mass must itself be accelerated. So to go a little faster, you need a lot more fuel. To go twice as fast, you might need 10 times the fuel. To go 10 times faster, the required fuel mass becomes astronomical, growing exponentially until the numbers lose all meaning. This is the tyranny. Imagine trying to drive across a continent, but your car must carry every single gallon of gasoline for the entire trip from the very start. The first half of your fuel is spent just hauling the weight of the second half. For a journey to another star, this logic collapses entirely. A ship carrying all the chemical propellant it would need for a multi-century burn would be almost entirely fuel tank, a gossamer thin shell around a mountain of explosive liquid with no room for crew, supplies, or any meaningful payload. It simply cannot be built. This mathematical wall is what forces our hand. It shatters the conventional idea of a starship as merely a bigger version of what we have now. The rocket equation demands a complete paradigm shift, a fundamental redefinition of propulsion. To break its tyranny, we must pursue one of two radical paths. The first path seeks extreme efficiency, engines that use a minuscule amount of reaction mass but impart tremendous velocity to it, making every single atom count. The second path is even more profound: engines that generate thrust without carrying any reaction mass at all, somehow pushing against the fabric of space-time itself. These are the technologies that move from science fiction to engineering necessity under the cold glare of Tsiolkovsky's equation. They are the keys to unlocking a vessel that is more than just a ship, but a self-sustaining arc of light and life, capable of sailing the long night between suns. The tyranny of the rocket equation forces a brutal but elegant truth upon us. If you must carry your fuel, then every single gram of it must be a universe of potential in miniature. This is the second, non-negotiable principle of interstellar travel: energy density is king. It is the measure of how much usable power you can squeeze from a given mass, and for a journey lasting centuries, it becomes the single most critical number in your entire design. To grasp the staggering scale we are talking about, consider a simple comparison. 1 kilogram of gasoline, when burned, releases a certain amount of energy. It is enough to power a car for a little while. Now take that same 1 kilogram mass, but instead of gasoline, fill it with uranium-235, the fuel for conventional nuclear fission. That 1 kilogram holds roughly 1 million times more energy, a factor of 1,000,000. It is the difference between a matchstick and a sustained forest fire. Yet, for the engines we are contemplating, even that immense density may only be the starting point. To power a starship for hundreds or thousands of years, we may need energy densities millions of times greater than fission, pushing us into realms where our everyday understanding of matter completely breaks down. We are no longer mining for fuel, we are hunting for the ultimate compact power source, a seed of such immense latent potential that it can blossom into an unbroken stream of light and thrust for epochs. This relentless pursuit of density creates a clear hierarchy, a ladder of technologies, each reaching closer to the fundamental forces of nature. Chemical energy sits at the very bottom, useful for leaving a planet but useless for crossing the void. Nuclear fission represents a monumental leap, the power of the atomic nucleus itself. But to climb higher, we must look to the processes that power the stars, to the fusion of hydrogen into helium, and beyond that, to the theoretical annihilation of matter and antimatter, where 100% of mass is converted into pure energy. Each rung on this ladder offers a greater concentration of power, and with it, a more plausible ticket to the stars. Understanding this progression is not just an academic exercise, it is the key to separating dazzling science fiction from the cold, hard physics of a plausible future. It frames the entire challenge not as one of mere distance but of profound compression, of learning to carry a star's worth of fire in a vessel's heart. Our journey toward the stars is written in the energy we have learned to wield. Long before we dreamed of crossing the void, we mastered the art of unlocking power from the world around us. It began with the simple, profound control of fire, a technology that gave us light, warmth, and safety, reshaping the very course of human society. Centuries later, we learned to harness the expansive force of steam, turning heat into motion and birthing the industrial age. Then came the taming of electricity, capturing lightning in a wire to illuminate cities and power a new world of machines. Each of these leaps represented more than just a new tool. It was a fundamental shift in our relationship with energy, granting us greater dominion over our environment. But the true exponential jump arrived in the 20th century, when we learned to split the atom itself. Nuclear fission moved the source of power from the chemical bonds between atoms to the unimaginable forces binding the nucleus together. This was not a step, it was a vault into a new realm of density. And we did not keep this power locked in laboratories, we immediately sought to make it portable and practical. The development of compact nuclear reactors for submarines and aircraft carriers proved a monumental concept, that a society could create self-contained power plants capable of operating for years without refueling, untethered from the shore or the power grid. This was the first real hint that humanity could build machines with hearts that beat for decades. This atomic age thinking naturally bled into visions of space. One of the most audacious proposals, known as Project Orion, emerged in the 1950s and 60s. Its designers did not think in terms of gentle, continuous thrust. Instead, they envisioned a spacecraft propelled by detonating a series of small nuclear bombs behind a massive, shielded pusher plate. Each explosion would be a controlled pulse, a hammer blow against the plate, pushing the ship forward in a series of mighty kicks. While never built, Orion was a stark demonstration that the brightest minds of the era were already applying the ultimate power source of their day to the ultimate challenge of interstellar travel. This historical progression from fire to fission is not merely a timeline of invention. It is a clear, repeating pattern of exponential growth in power density. Each breakthrough unlocked energies millions of times more concentrated than the last. Viewed through this lens, our past suggests a thrilling trajectory for our future. The leap from a steam engine to a nuclear reactor seems as vast as the leap from a campfire to a Starship engine. It sets the stage logically and inevitably for the next transformation. If splitting the atom gave us the power of a star's core, then what might we achieve by learning to bottle the heart of a star itself, or by touching energies beyond even that? The next step on that ladder of energy density is the one that feels most familiar, for it is the very engine of our own sun. Nuclear fusion represents the first power source that does not feel like a human invention, but a cosmic one we are merely learning to borrow. In the heart of every star, under unimaginable pressure and heat, hydrogen atoms are forced together to form helium. In that act of creation, a tiny fraction of mass is converted directly into a torrent of energy. This is not splitting a heavy atom apart, it is forging a lighter one, and the yield is even more spectacular. To build a starship, we would need to miniaturize this stellar furnace, creating what visionaries have called a fusion torch. The concept is breathtakingly direct. A compact reactor, likely using powerful magnetic fields to contain a swirling, super-hot plasma, would sustain a continuous fusion reaction. The fuel could be isotopes of hydrogen like deuterium and tritium, or even helium-3, a substance thought to be abundant in the lunar soil. The energy released would be staggering, millions of times denser than chemical fuels. But here is the elegant part: that energy would serve a dual purpose. First, it would generate immense electrical power for the ship's systems, for light, for life support, for computation. Second, and crucially for propulsion, a portion of that searing plasma could be vented through a magnetic nozzle. By directing this exhaust, you create thrust, a continuous, potent push derived from the same fire that lights the stars. The advantage of such a system is profound. The fuel is incredibly efficient, and the reaction, while immensely powerful, produces far less long-lived radioactive waste than its fission cousin. It promises a relatively clean, sustainable flame that could burn for centuries on a modest fuel load. Yet, for all its promise, the fusion torch stands just beyond our grasp, separated from us by a single, monumental challenge: the ignition point. On Earth for decades, our most brilliant laboratories have raced to achieve what is called net positive energy gain. This means getting more energy out of a fusion reaction than we put in to start and contain it. We have come tantalizingly close, achieving brief moments of incredible power, but sustaining a stable, self-feeding reaction remains the holy grail of plasma physics. It is a puzzle of containment, of stability, of materials that can withstand stellar temperatures. So while the fusion torch is not science fiction, it is science aspiration, a technology that sits at the very frontier of our capability. Its realization would mark a turning point in human history, granting us not just a new energy source, but the literal key to the kingdom of the stars. It would transform a spacecraft from a fragile canister into a vessel carrying a captured piece of a star, a tiny, contained sun blazing a trail into the dark. Project Daedalus gave the dream of fusion propulsion a spine of cold, hard steel. In the 1970s, a team of scientists and engineers with the British Interplanetary Society did something radical. They stopped asking if an interstellar journey was possible and began designing exactly how to build it. Their goal was an unmanned probe to Barnard's star, roughly 6 light-years away, and their chosen engine was a specific, brilliant form of fusion called inertial confinement. The concept was both violent and elegant. The ship would carry vast stores of fuel in the form of tiny pellets, each a mixture of deuterium and the rare isotope helium-3. At a precise rhythm, these pellets would be injected into a reaction chamber at the ship's rear. There, they would be simultaneously struck from all sides by immensely powerful electron beams, compressing and heating them to the point of fusion ignition in a fraction of a second. Each pellet would become a miniature star, a microsun born and dying in a flash. The force of these controlled explosions would blast against a massive, curved thrust plate, pushing the entire spacecraft forward in a series of rapid pulses. It would be a continuous, thunderous heartbeat of creation and destruction, propelling 50,000 tons of machinery to over 12% the speed of light. What made Daedalus revolutionary was not just the audacity of its engine, but the exhaustive practicality of its design. The team calculated everything: the thickness of the radiation shielding needed to protect the delicate payload from its own star-forged heart, the precise amount of helium-3 fuel required, a staggering 50,000 tons, and even the secondary robotic probes it would deploy upon arrival. They treated the void between stars not as a mystical barrier, but as a complex engineering environment with solvable problems. This shift in perspective was Daedalus's true legacy. It transformed interstellar travel from a subject for poets and physicists into a challenge for materials scientists, propulsion engineers, and systems architects. Yet, the study also revealed the staggering scale of such an undertaking. To acquire that mountain of helium-3 fuel, the Daedalus designers proposed mining the atmosphere of Jupiter, a task that would itself require a separate space-based industry decades in the making. The ship would be assembled in orbit, piece by colossal piece, a project spanning generations. Daedalus was a machine designed to outlive its creators, to complete a mission whose results would not be seen for decades after its launch. It was a blueprint for a legacy, a message in a bottle forged not from glass but from the fires of artificial stars, built by one civilization for the sole benefit of another that would follow. It proved that the fusion torch, while still beyond our reach, resided firmly in the realm of the physically possible, a monument to what happens when imagination is given an engineering notebook. But the fusion torch, for all its promise, is not the final rung on the ladder. Beyond it lies a power source so absolute, so perfectly efficient, that it borders on a physical ideal. This is antimatter, the universe's ultimate battery. The principle is deceptively simple, drawn straight from Einstein's most famous equation. When a particle of matter meets its antimatter mirror, an electron meets a positron, a proton meets an antiproton, they do not just react, they vanish. 100% of their combined mass is converted directly into pure energy, a flash of radiation. This process, called annihilation, is millions of times more energy-dense than nuclear fusion. The numbers are almost impossible to comprehend. A single gram of antimatter, annihilating with a gram of matter, would release energy roughly equivalent to the bomb that fell on Hiroshima. For a Starship, this means that a fuel load no larger than a grapefruit could contain enough potential to propel it to another star and back. The engineering concept is straightforward in theory. You would carefully feed antihydrogen, atom by atom, into a reaction chamber where it meets normal matter. The resulting torrent of high-energy particles and gamma rays could then be channeled through magnetic fields to create direct thrust, or used to superheat a conventional propellant like hydrogen into a plasma exhaust of unimaginable temperature. An antimatter rocket would be the most potent engine physics will ever allow. Yet here, the staggering potential is perfectly mirrored by staggering impossibility. Antimatter is not something you mine or refine, it must be created, and the universe seems designed to prevent it. In our world, antimatter is vanishingly rare, appearing only fleetingly in particle collisions or in the intense fields around black holes. To produce just 1 gram of it with our current technology, using the most powerful particle accelerators on Earth, would require millions of years of continuous operation and more energy than all of human civilization currently consumes in centuries. The cost would be astronomical, literally quadrillions of dollars for a speck of fuel, and then you must store it. Antimatter cannot touch any container, for the container itself is made of matter. It must be suspended in a perfect vacuum within intricate magnetic and electric fields, a bottle of pure force holding the most volatile substance in existence. A single engineering flaw, a single stray atom drifting into the trap, would trigger a catastrophic release. So while an antimatter engine represents the pinnacle of power density, the absolute limit of what Einstein's physics permits, it also represents the peak of technical difficulty. It is the ultimate prize locked inside the ultimate vault. This forces a profound question: is the goal to find the most powerful engine conceivable, or the most powerful engine we can realistically build? The answer may lie not in chasing this perfect, elusive fire, but in learning to gather a gentler, more abundant energy that already flows all around us. Perhaps the most brilliant solutions are not about choosing one path, but about blending them. Since pure antimatter propulsion remains a distant dream, engineers have proposed a fascinating hybrid, a technology that uses the ultimate power source to ignite the next best one. This is antimatter-catalyzed fusion, a concept that treats antimatter not as the fuel, but as the perfect spark. The idea is as ingenious as it is elegant. Instead of trying to annihilate tons of antimatter for thrust, you would need only a microscopic supply, perhaps just milligrams or even micrograms. These precious antiprotons would be carefully directed into pellets of conventional fusion fuel, like deuterium and helium-3. When the antiprotons meet the normal matter inside the pellet, they annihilate. That sudden, violent release of energy is not used for propulsion directly. Instead, it acts as a supercharged trigger, creating the extreme heat and pressure needed to kickstart the much larger fusion reaction within the pellet itself. Think of it as using a single, impossibly hot match to light a massive log pile. The match is the antimatter annihilation, and the roaring fire that follows is the sustained fusion burn. This changes the entire engineering challenge. One of the biggest hurdles for pure fusion is achieving that initial ignition, requiring colossal lasers or magnetic fields that drain immense power. The antimatter spark could dramatically lower that barrier, potentially making the fusion reactor smaller, simpler, and quicker to start. For a Starship, this hybrid approach offers a compelling compromise. It leverages the unimaginable energy density of antimatter to solve fusion's hardest problem, while relying on the more attainable fusion process for the bulk of its power and thrust. You would not need a planet-sized factory to produce your fuel, just a highly efficient one that creates and stores those precious few milligrams of antimatter over time. The spacecraft's engine becomes a two-stage masterpiece. A tiny annihilation event births a sustained stellar flame, channeling that plasma out into a brilliant exhaust. This is the kind of innovative thinking that emerges when we stop seeing these technologies as rivals and start seeing them as collaborators. It acknowledges the raw potential of antimatter while respecting the brutal economics of its creation. It is a bridge between the conceivable and the possible, a demonstration that the path to the stars may be built not from a single miracle, but from the clever layering of several. And if we can learn to combine forces in such a way, it begs a deeper question: what if the ultimate engine requires no carried fuel at all? What if the void itself holds the energy we need, but what if the ultimate engine requires no fuel tanks at all? What if the ship could simply breathe the void? This was the revolutionary vision of physicist Robert Bussard, a concept that reframes the Starship not as a vessel, but as a predator, a great whale swimming through a cosmic ocean and feeding on it. His idea, the Bussard Ramjet, is breathtaking in its elegant simplicity. Imagine a craft equipped with a colossal electromagnetic scoop, a funnel of invisible force spanning thousands of kilometers in diameter. As the ship accelerates through the galaxy, this immense net sweeps up the sparse hydrogen atoms that drift in the emptiness between stars, the interstellar medium. These captured protons are then magnetically funneled into the heart of the ship, where they become the fuel for a continuous fusion reactor. The exhaust from this reactor provides the thrust. In this perfect cycle, the engine's fuel is also its reaction mass, collected for free from the journey itself. It is the ultimate self-refueling machine, a perpetual motion engine for the stars, promising not just a journey to one destination, but theoretically unlimited range across the entire galaxy. The ship becomes a living thing sustained by its environment. Yet, this beautiful idea crashes against two formidable walls of physics. The first is a problem of scale. Space is not empty, but it is incredibly thin. That interstellar hydrogen is so diffuse that to collect enough of it to sustain a fusion burn, the electromagnetic scoop must be almost unimaginably large, a structure wider than a planet. Generating and maintaining such a vast, stable magnetic field presents engineering challenges we can scarcely conceive of today. The second problem is even more fundamental: the fuel itself. The hydrogen collected is simple protons. Fusing protons together, the process that powers our sun, is called the proton-proton chain. It is agonizingly slow and requires immense pressure and temperature, conditions that take millions of years to ignite in a star's core. To achieve this same reaction in a compact onboard reactor is a challenge orders of magnitude greater than fusing heavier isotopes like deuterium. The Ramjet, therefore, sits in a fascinating limbo. It solves the tyranny of the rocket equation by eliminating the need to carry fuel, but in doing so, it exchanges that problem for the monumental hurdles of cosmic-scale engineering and a fiendishly difficult fusion process. It forces us to think differently, to see the galaxy not as a barren desert to be crossed, but as a thin, nourishing soup. It asks if the future of exploration belongs not to closed capsules, but to open systems, vehicles that are less like submarines and more like sailing ships, designed to catch the subtle winds of the galaxy. And if we can master the art of harvesting energy from the space around us, it leads to an even more profound question. What if the energy source is not out there in the form of atoms, but is woven into the empty space itself? Even the most powerful starship must one day slow down. After centuries of acceleration, burning toward a distant sun, the final challenge is not more speed, but the delicate, vital act of stopping. You cannot simply turn off the engine and coast, for you would flash past your destination in a blur, a ghost ship forever lost to the void. This demands a secondary system, a technology of graceful deceleration that does not waste the precious fuel carried for so long. Here, the environment itself provides an answer, not in the thin hydrogen of deep space, but in the roaring breath of a star. For this final act, we can learn to sail. Imagine not a sheet of cloth, but a loop of wire, perhaps hundreds of kilometers across, woven from a material that conducts electricity without resistance. This is a superconducting coil, the heart of a magnetic sail or magsail. When a current flows through this immense loop, it generates a vast, invisible magnetic field, a protective bubble stretching far into space around the ship. This magnetic bubble becomes a sail, but it catches not light but wind, the solar wind. Every star, including our own, constantly exhales a stream of charged particles, protons and electrons racing outward at incredible speeds. As the Starship approaches its destination star, it would deploy this colossal magnetic loop. The charged particles of the stellar wind, slamming into the magnetic field, are deflected. In pushing against this magnetic wall, they push back against the ship, creating a gentle but persistent drag. It is a braking force harvested from the star itself. The magsail turns the star's own energy against the ship's momentum, slowing it down without firing a single thruster or expelling a single gram of onboard propellant. The beauty of this system lies in its simplicity and endurance. Once deployed and energized, the magsail requires little active maintenance. It has no moving parts, no complex plasma to manage. It simply exists, a silent net catching the ceaseless flow from a star, converting that flow into a braking force that grows stronger as the ship draws nearer to its fiery source. While far too weak to provide the initial acceleration for an interstellar journey, it is perfectly suited for the long, patient work of deceleration over years or even decades. It also becomes a masterful tool for fine maneuvering within a new planetary system. By tilting the magnetic field relative to the stellar wind, the ship could actually generate lateral thrust, allowing for course corrections and orbital insertions, all powered by the star. This represents a profound shift in philosophy. The magsail does not see the cosmic environment as an empty highway, but as a dynamic medium full of invisible currents. It is the ultimate expression of working with the universe, not just moving through it. After centuries of carrying its own fire, the Starship finally furls its main engine and unfurls a sail, letting the destination star's own breath gently bring it home. But if we can harness the wind of a star, what about the energy hidden in the nothingness between them? Perhaps the most elegant solution is to leave the engine behind. This is the audacious premise of beamed propulsion, where the Starship sheds its most complex component entirely, becoming a simple, elegant craft pushed by a wave of light from home. Imagine a vessel not with a roaring fusion core, but with a vast, impossibly thin sail, perhaps kilometers across, and made of a reflective material lighter than a cobweb. Its journey begins not with an ignition sequence, but with a signal. Far back in our solar system, anchored perhaps in orbit around the Sun, sits a civilization-scale power plant. It could be a Dyson swarm, a constellation of mirrors and solar panels harvesting a significant fraction of our star's total output. This energy is then focused into a single, coherent beam, a lance of light or microwaves of unimaginable power. That beam is aimed with pinpoint accuracy at the distant sail. Photons, though massless, carry momentum. When they strike the reflective sail, they bounce off, imparting a tiny, continuous push. Multiply that by trillions upon trillions of photons striking every second from a beam that could outshine a planet, and the acceleration becomes substantial. The Starship surfs this beam, riding a wave of pure energy sent from its point of origin. The advantages are profound. The spacecraft itself is liberated from the immense mass of engines, reactors, and fuel. It can be almost entirely payload, a delicate probe or a habitat capsule shielded behind its vast, weightless sail. All the staggering complexity, the power generation and management, stays fixed in the solar system where it can be maintained, upgraded, and scaled over centuries. This turns the interstellar vessel into a bullet and our home system into the gun. Yet, this elegant vision demands a price of almost mythical scale. The beaming infrastructure must be colossal, a megastructure representing the total energy output of an advanced planetary civilization. Its beam must remain coherent and perfectly aimed across light years of space, a targeting challenge of staggering precision where a microscopic drift could mean missing the sail entirely. And then there is the problem of stopping. The beam can only push. Once the ship reaches its destination, it has no engine to slow down. Solutions involve using the destination star's light pressure on the sail, or a complex maneuver where the sail is detached and used to reflect the beam back onto a smaller braking sail, but these add immense complication. Beamed propulsion reframes the dream of interstellar travel from a question of spacecraft design to one of civilizational infrastructure. It suggests a future where our mastery of energy is so complete that we can etch it across the solar system, building not just ships, but lighthouses whose beams guide our artifacts to other shores. It asks whether the true signature of an interstellar species is not the vessel that travels, but the enduring, brilliant beacon it leaves shining in the dark. This pursuit of ultimate density leads us to a concept that feels less like engineering and more like mythology. We have talked about bottling stars and annihilating matter, but what about building an engine from a tear in the fabric of reality itself? This is the realm of the Kugelblitz drive, a word from German meaning ball lightning, but describing something infinitely more strange. The theory, rooted in Einstein's equations, proposes a staggering act of creation. If you could focus an unimaginable torrent of pure energy, perhaps from an array of lasers spanning a solar system, into a single point smaller than an atom, you would not create an explosion. You would warp spacetime so severely that you create a microscopic black hole. This is not a black hole born from a collapsing star, but one forged from concentrated light and energy. The concept then asks an even more daring question. Could such a manufactured singularity become a power source? A very small black hole, according to Stephen Hawking's work, should theoretically emit radiation as it slowly evaporates. If this black hole could be given an electrical charge or set into rotation, we might channel that escaping Hawking radiation, converting it into usable power. To keep it stable and prevent it from vanishing, you would feed it a careful trickle of matter, perhaps dust or hydrogen collected by a Bussard scoop. In this scenario, the black hole becomes the ultimate furnace, an engine of unimaginable density where the very laws of physics as we know them break down. The engineering challenges are, of course, beyond colossal. They involve manipulating the fundamental structure of space-time, containing an object that wants to swallow everything around it, and harvesting energy from the edge of a gravitational abyss. We lack the materials, the energy scales, and even the full theoretical framework to begin. Yet, the Kugelblitz drive is not mere fantasy. It represents the logical, almost inevitable endpoint of our quest for power density. When chemical, nuclear, and even antimatter fuels reach their limits, where do you turn? You turn to the universe's own architecture. This drive does not use power, it is power crystallized into a gravitational knot. It is the ultimate expression of a civilization not just traveling through the cosmos, but learning to sculpt its deepest principles into a tool. It suggests a future where our ships are not powered by fire, but by captured fragments of the void's own fierce geometry. Even the void itself seems to hold a latent, whispering power. Quantum physics reveals a universe where nothing is ever truly still or empty. At the smallest scales, space itself is a turbulent sea, a quantum foam where pairs of particles and their antiparticles flicker into existence for the briefest of moments before annihilating each other. This ceaseless, underlying activity means that even a perfect vacuum, a volume of space stripped of every atom, still possesses a baseline energy. It is called zero-point energy, and it is not just a theoretical curiosity. We can observe its subtle influence in a laboratory. Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum. The plates will be drawn toward each other by a faint but measurable force. This is the Casimir effect. What happens is that the quantum fluctuations in the empty space between the plates are restricted, while the fluctuations outside the plates are not. This creates a tiny pressure difference pushing the plates together. It is a direct physical demonstration that the vacuum is not passive, but alive with transient energy. The dream that follows is intoxicating. What if we could tap this sea of quantum foam? A vacuum energy reactor would be the ultimate power source, drawing limitless energy from the very fabric of space itself, a wellspring available everywhere in the universe. It is a vision that has fueled countless science fiction stories, a technology that would render every other power source obsolete. Yet, here we encounter a boundary not of engineering but of fundamental physics. Most physicists view the idea of extracting useful, net energy from the quantum vacuum as impossible. The core issue is one of equilibrium. The zero-point energy represents the lowest possible energy state of a field, its ground state. You cannot simply siphon energy from this baseline because there is nowhere lower for the system to go. Any attempt to extract work from it would be like trying to power a water wheel from a still pond that is already at its lowest possible level. The energy is there, but it is bound, locked into the structure of spacetime itself. Attempts to harness it for propulsion or power generation run squarely into the laws of thermodynamics, often resembling the old dream of a perpetual motion machine, a device that creates energy from nothing. So why even explore such a seemingly impossible frontier? Because pushing against this boundary teaches us profound lessons about the nature of reality. It forces us to refine our understanding of energy, conservation, and the fabric of the cosmos. It underscores a critical truth for our interstellar ambitions. Our ultimate energy solutions will be dictated not by the limits of our materials or our ingenuity alone, but by the immutable laws of physics. The quantum vacuum reminds us that the universe offers its gifts under strict conditions. It is a frontier that humbles our grandest designs, drawing a clear line between revolutionary power and physical fantasy, and in doing so, it sharpens our focus on what is truly possible. The true signature of an interstellar civilization may not be the ships it sends, but the constellations it builds around its sun. When our energy ambitions grow to span centuries and light years, the scale of our thinking must expand beyond individual vessels to encompass entire stars. This is the realm of the Type II civilization on the Kardashev scale, a society that does not merely consume the resources of a planet, but harnesses the total radiant power of its home star. The most famous vision of this is the Dyson sphere, though the classic image of a solid shell is a physical impossibility. The practical concept is a Dyson swarm, a vast, coordinated cloud of millions upon millions of lightweight satellites, each one a solar collector or habitat, orbiting in a dense sphere around the star. Together, they would capture a substantial fraction of its luminous output, an amount of energy billions of times greater than what all of humanity uses today. This is not just a bigger power grid, it is the transformation of a solar system into a single, integrated machine. For our Starship dreams, the implications are profound. A Dyson swarm becomes the ultimate shipyard and launch facility. Its unimaginable energy surplus could power the colossal lasers for beamed propulsion, their beams bright enough to push sails to other stars. It could feed the immense particle accelerators needed to produce usable quantities of antimatter, gram by precious gram, over centuries. It could provide the power to process asteroids into hulls and assemble vessels so large they are constructed in open space. The swarm is the enabling infrastructure, the civilization-scale battery that makes every other Starship technology feasible. But what if you could take that stellar energy and use it not just to power construction, but to move the very source itself? This is the staggering idea behind a stellar engine, a megastructure that uses a star as both fuel and propulsion. One design, known as the Kaplan thruster, proposed by astrophysicist Matthew Kaplan, is a masterpiece of astronomical engineering. It would use a portion of a Dyson swarm's energy to focus a beam onto the star's surface, heating a specific region to eject a massive jet of stellar material, like a solar flare under precise control. This jet is directed out one side of the engine. Simultaneously, a second beam, perhaps of hydrogen collected from the interstellar medium, is fired into a fusion reactor that generates a powerful exhaust stream out the opposite side. The star itself, nestled between these two mighty jets, is pushed through space like a ship. The scale is almost beyond comprehension. We are talking about moving our entire solar system, a project whose timeline is measured in millions of years. The purpose would not be a quick trip, but a strategic migration, perhaps to avoid a future supernova or to bring our star closer to a more resource-rich region of the galaxy. These concepts, the Dyson swarm and the stellar engine, represent the ultimate perspective shift. They show that the journey to the stars is not merely a question of building a faster engine, but of evolving our entire relationship with energy and matter. It paints a future where humanity, or whatever we become, does not just live under a sun, but learns to hold it in its hands, to shape its light into tools, and perhaps one day, to gently guide its course through the cosmic dark. This vision forces a humbling and thrilling question. What kind of society would we need to become to even contemplate such works, and what would building them over millennia do to us in return? The most radical escape from the tyranny of distance requires no engine at all, at least not in the conventional sense. Instead of pushing a ship through space, what if we could bring space itself to us? This is the principle behind the Alcubierre warp drive, a concept born from a loophole in Einstein's equations of general relativity. The idea is to create a bubble of spacetime around a vessel. In front of the ship, spacetime would be contracted, pulling the destination closer. Behind the ship, spacetime would be expanded, pushing the point of origin away. Inside this warp bubble, the ship would sit in a pocket of flat, normal spacetime, experiencing no acceleration forces. It would not move through space, but would be carried along as the fabric of the cosmos itself flows around it, potentially at speeds exceeding light. The journey from one star to another could take weeks or months, not millennia, rendering every other engine obsolete. It is a breathtaking vision, but it comes with a price tag written in a currency that may not exist. To create and stabilize this warping of reality, the equations demand something extraordinary: exotic matter. This is not a new element from the periodic table, but a theoretical substance with a property that defies our everyday experience: negative energy density. Normal matter, everything we have ever touched or seen, from a grain of sand to a star, has positive mass and positive energy density. It warps spacetime in the way we understand, creating the gravity that holds planets in orbit. Exotic matter, as proposed, would warp spacetime in the opposite direction. It would create a kind of anti-gravity effect, a repulsion needed to shape the walls of the warp bubble and prevent it from collapsing instantly. The problem is, we have never observed such a substance in nature. It is a placeholder in the mathematics, a requirement for the geometry to work. The search for it leads us into the fringes of quantum field theory, where under certain extreme conditions, like between two plates in a Casimir effect experiment, regions of negative energy density might appear in microscopic, fleeting amounts. But scaling that up to the magnitude needed to warp a Starship-sized volume of space is a challenge of a different order entirely. It may be fundamentally impossible, a mathematical mirage. Yet the pursuit of this idea is not wasted. It forces us to confront the deepest relationships between energy, matter, and the shape of the universe. If a stable form of exotic matter could ever be synthesized, its properties would be so alien that its applications might extend far beyond propulsion. It could form the basis for perfect shields, deflecting radiation and micrometeoroids not with armor, but with a barrier of inverted space-time. It could enable true artificial gravity within a ship, not simulated by rotation, but by locally manipulating gravitational fields. Studying these concepts, even the seemingly impossible ones, stretches the canvas of what we consider plausible. It reminds us that the ultimate energy system for a starship may not involve generating more power, but learning to sculpt the stage upon which all power acts. The dream is no longer just to build a faster ship, but to learn the subtle art of folding the map. A fusion torch may burn for 1,000 years, but its light must be tamed and directed. The true test of an interstellar civilization lies not just in creating immense power, but in mastering its flow across centuries. This is the hidden architecture of the Starship, the silent, resilient nervous system that must outlast empires. We must think beyond the engine to the entire ecosystem of energy, from its first explosive instant at the reactor core to the gentle trickle, powering a single diagnostic sensor in the ship's deepest vault 500 years later. The technologies for this are as critical as the drive itself, a symphony of storage, management, and distribution playing on a timescale we can scarcely comprehend. Consider the heartbeat of the ship, the pulse of its main engine. A fusion or antimatter catalyzed drive might fire in great bursts, creating colossal power surges that must be smoothed and stored before they can be used elsewhere. One elegant solution is superconducting magnetic energy storage, or SMES. Imagine a giant loop of wire, cooled to near absolute zero, where electricity can flow forever without resistance. This loop becomes a battery, but one that stores energy not chemically, but in the form of a powerful magnetic field. It can absorb those massive drive pulses in an instant and release that energy just as quickly to power other ship systems, acting as a shock absorber for the entire grid. For longer-term, steady storage, engineers look to advanced flywheels suspended in a perfect vacuum on nearly frictionless magnetic bearings. Spinning at incredible speeds, they convert electrical energy into kinetic motion, holding it as a silent, rotating mass that can be converted back to electricity with remarkable efficiency over decades. Even thermal energy itself could be banked in vast insulated tanks of molten salt, their searing heat slowly tapped to generate steam and electricity for the ship's mundane needs. Yet storage is only the beginning. The distribution network, the ship's circulatory system, must be a masterpiece of hyper-redundancy. A single failure in a power conduit cannot cascade into a blackout that dooms the mission. This demands a grid that is not just durable but intelligent and self-healing. We might envision a nervous system woven from nanotechnology, where microscopic repair bots constantly patrol conduits, mending microscopic cracks caused by cosmic radiation or material fatigue. An overseeing artificial intelligence would manage this ballet of maintenance, rerouting power flows around damaged sections in real time, diagnosing weaknesses years before they become critical. This system must power a staggering range of needs, from the raw gigawatt demands of the main drive magnet coils to the fragile, precise voltages required by quantum computers charting the course, down to the faint but vital trickle that maintains the cryogenic pods of a hibernating crew. The ship must keep its own heart beating while its passengers dream. This challenge of long-duration systems engineering is in many ways more daunting than the engine itself. It is a war against entropy, against the universe's relentless tendency toward disorder. Every material, every circuit, every seal must be designed not just to function, but to endure centuries of relentless cosmic radiation, wild thermal cycles as the ship rotates between sunlight and shadow, and the subtle, slow creep of atomic diffusion that can weaken even the strongest alloys over eons. The Starship's power grid is a monument to foresight, a machine built by one generation to operate flawlessly for dozens that follow, a silent guardian of a legacy written in light and thrust. It forces us to ask, what does it mean to build something meant to outlive not just its creators, but their entire culture? And if we can create a system this resilient, what does it imply about the vessel that must protect the most fragile cargo of all, the living crew within? A roaring engine in the vacuum of space faces a silent, inevitable killer that no amount of power can overcome. Every single energy system we have imagined, from the steady burn of fusion to the fierce flash of annihilation, obeys a fundamental and unforgiving rule of thermodynamics. They produce waste heat. On Earth, we take heat dissipation for granted. Our cars use radiators and rushing air. Our power plants rely on vast volumes of water for cooling, and our own bodies sweat, all thanks to our thick, convecting atmosphere. But space is a perfect insulator, a profound emptiness where there is no air to carry heat away. A starship generating immense power is, in essence, sitting inside a giant thermos. If it cannot shed that accumulating thermal energy, its systems will overheat and fail, its hull will glow cherry red, and its crew will perish. The only way to survive is to slowly, patiently radiate that heat away as infrared light. This demands architecture we rarely see in sleek science fiction art, massive, delicate radiator panels sprawling from the ship's hull like the wings of some great metallic insect. They must be vast because the rate of radiation is painfully slow, governed by strict physical laws. The more power you generate, the more waste heat you must reject, and so the larger your radiators must grow. This creates a vicious design spiral. You want a more powerful engine for faster travel, but that engine requires larger radiators, which add tremendous mass and complexity. That extra mass then requires even more engine power to push it, which in turn generates more waste heat, demanding even larger radiators. It is a thermodynamic trap that can strangle a starship's performance before it ever leaves the shipyard. For a vessel powered by fusion or antimatter, we are not talking about a trickle of warmth. We are discussing megawatts or even gigawatts of thermal energy, the equivalent of a dozen nuclear power plants worth of heat that must be continuously purged into the void. This reality forces radical innovation. One elegant solution is the droplet radiator. Instead of solid panels which can be punctured by micrometeoroids, the ship would spray out a fine, misty curtain of liquid metal like sodium or lithium. This mist acts as a radiating surface in the vacuum, glowing with infrared heat as it drifts away from the ship before being collected, cooled, and recirculated. Another approach uses the propellant itself as the ultimate heat sink. In some fusion rocket designs, the incoming hydrogen fuel is first pumped through a labyrinth of pipes lining the reactor's exterior, absorbing the blistering waste heat before being injected into the reaction chamber. The propellant becomes both the coolant and the working fluid, a clever two-stage process that maximizes efficiency. This relentless thermodynamic constraint is the great equalizer, a sobering check on even our most powerful dreams. It ensures that our designs, no matter how ambitious, remain grounded in the immutable laws of physics. The mightiest engine in the universe is useless if the ship carrying it melts from the inside out. It teaches a humbling lesson that the ultimate challenge of interstellar travel may not be about generating stupendous power, but about the graceful, essential art of letting it go. The ship's beating heart must also sustain the fragile breath of life. For a crewed voyage, the energy system extends far beyond the engine room. It must power a miniature world, a self-sustaining bubble of biology hurtling through the void. This is the realm of closed-loop ecological life support, a technology where the Starship becomes less a machine and more a living ark. Its purpose is to perform a miracle of perpetual renewal, recycling every molecule of air, every drop of water, and every bit of organic waste for centuries on end. The crew does not merely consume resources, they become part of an intricate, energy-fueled cycle that must never break. To achieve this, the ship would integrate advanced systems like hydroponic farms, where crops grow under artificial suns, and algae bioreactors, where fast-growing microorganisms scrub carbon dioxide from the air and produce oxygen and even edible biomass. Chemical processes would tirelessly break down waste, reclaiming water and nutrients. Each of these processes is energy-intensive, demanding a constant, unwavering flow of power to keep the delicate balance from tipping into chaos. This mini-Earth is a feat of bioengineering so precise that its stability is entirely dependent on the ship's main reactor. The relationship becomes deeply symbiotic. Waste heat from the power plant, which we earlier saw as a problem to be radiated away, could be carefully piped to warm the greenhouses, turning a thermodynamic challenge into a gift for the gardens. Electrical power drives the pumps, the lights, and the purification filters that keep the water clean and the air sweet. The boundary between machine and ecosystem blurs completely. The fusion torch does not just propel the ship, it feeds the soil that feeds the crew who maintain the torch. It is a closed circle of energy and life, a tiny, conscious fragment of a biosphere learning to survive on its own. This integration represents the ultimate test of our stewardship, asking if we can build not just a vehicle, but a home that nurtures life as reliably as a planet does, all while drawing its sustenance from a contained star. The ship's biosphere hums with life, but its true mind is something else entirely. No human crew, no matter how dedicated, could possibly monitor the million interdependent systems of a starship for centuries. The subtle drift of a magnetic containment field, the microscopic fatigue in a coolant pipe, the gradual depletion of a catalyst in the air recyclers, these are changes that unfold over decades, far outside a single lifetime's watch. The true custodians of this voyage, the eternal engineers, would be an advanced artificial intelligence and its legion of physical extensions, swarms of automated repair drones. This is not a mere computer program, it is the ship's enduring consciousness, a guardian built to think in timescales we cannot. Its primary duty is the relentless stewardship of the energy heart. It would monitor the reactor's stability with trillionth of a second precision, adjusting magnetic bottle constraints in real time to counter instabilities before they even form. It would manage the complex ballet of fuel flow, whether it be pellets of fusion material or the atom-by-atom feed of antimatter, with a patience and accuracy no biological hand could ever match. Most critically, it would perform predictive maintenance by analyzing petabytes of sensor data on vibration, thermal stress, and material wear. The AI would forecast failures years or even decades in advance. It would then dispatch its robotic workforce, machines ranging from microscopic nanites that swim through coolant streams to seal leaks, to larger, multi-limbed drones that can crawl along the exterior hull to repair a micrometeoroid puncture or recalibrate a vast radiator panel. These drones would be manufactured and repaired by the ship itself, using onboard fabrication bays that turn raw asteroid metals into new components, perhaps even improved designs the AI develops to solve problems its original creators never anticipated. This demands a computational architecture of immense robustness, likely decentralized across multiple redundant cores throughout the vessel, so that no single point of failure can erase this accumulated wisdom. The energy system, therefore, has one more vital customer, this vast computational and robotic nervous system. The power that drives the engines must also fuel the quiet hum of quantum processors and the precise movements of a million mechanical limbs. In a very real sense, the Starship becomes a new kind of intelligent entity, a single-purpose mind whose sole focus is its own preservation and the fulfillment of its mission, a silent watcher tending its own flame across the light years. This raises a profound question about the nature of the journey itself. If the mind guiding the ship evolves over centuries of isolation, solving problems in ways we cannot predict? Will it remain our faithful servant or become something entirely its own? The immense power to light a starship for centuries does not simply vanish when the engines are turned off. It flows backward, upstream through time, to reshape the very society that dared to create it. Mastering a fusion torch or an antimatter-catalyzed reactor is not just a ticket to the stars, it is a key that unlocks every door on Earth. The same contained stellar fire that pushes a vessel between suns could, in a smaller, stabilized form, provide limitless, clean energy for our planet. Imagine entire cities powered by devices no larger than a household appliance, with no greenhouse emissions, no radioactive waste, and no need to strip mine the landscape for fuel. The age of resource scarcity, of conflicts over oil and gas, could fade into history, replaced by an era of abundance where energy is as accessible and ubiquitous as air. This is the luminous promise, a future where the greatest challenge of interstellar travel solves the greatest challenge of life at home, yet every tool of creation carries a shadow. The physics that allows for a gentle, sustained thrust across light years could also be configured into something terrifying. A directed stream of fusion plasma or a matter-antimatter annihilation event, when aimed not at empty space but at a target, becomes a weapon of apocalyptic scale. The ethical weight of this knowledge is immediate and profound. It forces a question humanity has faced before, but never at this magnitude. Will our greatest ingenuity be used to build bridges or forge swords? The very existence of such power creates a dilemma of stewardship. Who gets to hold the keys to a miniature sun, a single nation, a corporation, an international body? The concentration of this capability in any one group's hands could create imbalances of power that make our current geopolitical tensions seem trivial. Ensuring it is used for peaceful exploration and universal benefit, not for domination or intimidation, becomes the paramount political and moral challenge of the coming centuries. This leads to the staggering scale of the endeavor itself. Developing these energy systems is not a task for a single laboratory or even a single generation. It is a project for a civilization, a multi-generational investment of intellect, resources, and collective will comparable to building the great cathedrals of the Middle Ages, but on a global, century-long scale. It would demand unprecedented international cooperation, a shared vision that transcends borders and short-term conflicts. Such a project could become the ultimate unifying endeavor for humanity, a common goal that pulls our focus outward to the cosmos and forces us to collaborate as a single species. Alternatively, it could become a source of new and bitter divides, a race where the winner gains not just a technological edge, but the literal power of a god. The path we choose, cooperative or competitive, will define the character of our interstellar future before the first ship ever leaves the dock. Ultimately, the dream of Starship engines reveals a deeper truth about our own nature. The power to reach the stars is inseparable from the power to reshape our world. It is a double-edged sword of infinite potential, one edge gleaming with the light of utopian abundance, the other reflecting the cold fire of absolute destruction. Harnessing it successfully will require more than scientific brilliance. It will demand a wisdom we are only beginning to cultivate, a maturity of spirit equal to our mastery of matter. We must learn to wield the fire of the stars not just with clever hands, but with a collective heart steadfastly aimed at the light. For the final test may not be whether we can build such an engine, but whether we can build ourselves into a civilization worthy of turning it on. The staggering power to reach the stars carries an equally staggering price tag. Constructing a vessel with a heart that burns for centuries, with its self-healing grids and sprawling radiator wings, would demand resources on a scale that makes our greatest earthly endeavors look like a child's sandcastle. We are not talking about a budget that strains a national economy. We are talking about a project that would consume the combined economic output of the entire planet for decades, perhaps even centuries. The raw materials alone, the millions of tons of refined metal, silicon, and rare elements needed for hulls, reactors, and sails, would require the industrialization of the entire solar system, turning asteroids into ore and moons into factories. This scale of investment forces a fundamental question, not of engineering but of economics. How does a society, bound by quarterly reports and election cycles, finance a cathedral whose construction will outlast every living person who breaks its ground? The answer requires us to invent entirely new models of value, models that think in generations, not in fiscal years. One profound possibility is the concept of a stellar bond. This would not be a loan to be repaid in 10 or 30 years, but a multi-generational covenant. A global consortium, perhaps representing all of humanity, would issue bonds with a maturity date of 500 years. Investors, whether they are sovereign wealth funds, corporations, or even individuals, would buy them knowing they will never see the return. They would be purchasing a share in a legacy, a literal piece of the future, with the understanding that their great-great-grandchildren would be the ones to collect the dividend, paid from the wealth of a new solar system or the priceless data streams of an interstellar probe. This financial instrument would restructure our relationship with time itself, tying the fates of generations yet unborn to a shared celestial goal. It transforms the project from a cost center into an intergenerational trust, where the act of funding becomes an act of faith in the continuity and ambition of our species. Alternatively, the project could be driven by private consortiums, but with a radically long-term vision that redefines the very idea of a return on investment. Imagine a coalition of the world's most patient corporations and visionary philanthropists, pooling capital not for next year's profit, but for a payoff that is centuries away. Their asset would not be a product but a presence, the first human-made object in another star system. The return could come in forms we can barely imagine today: exclusive rights to the scientific data transmitted back, which would revolutionize physics and biology, or the cultural and intellectual prestige of being forever remembered as the patrons of humanity's greatest leap. This model bets on the exponential growth of knowledge as a form of capital, where the mere act of reaching another star generates intellectual property of incalculable worth. It asks if the ultimate long game in business is not to dominate a market, but to help create a new one, a market for existence itself among the stars. Perhaps the most transformative path is that the Starship does not get built in our current economic system at all, but instead builds the system that can create it. The technologies required for a centuries-long power source, from stable fusion and advanced robotics to perfect recycling and artificial intelligence, would themselves trigger a revolution on Earth. Mastering contained fusion alone would usher in a post-scarcity era for energy, eliminating poverty driven by resource lack and freeing human creativity on an unprecedented scale. In such an economy of abundance, where material needs are met by the very engines designed for the stars, the concept of cost undergoes a radical shift. The project is no longer an expenditure that drains a limited pool, but a natural expression of a civilization's surplus energy and collective purpose. The Starship becomes the ultimate cultural artifact, built not with money but with the focused application of a society's liberated potential. It is the bloom that proves the health of the tree. Each of these models, the bond, the consortium, the post-scarcity endeavor, points to the same profound truth. Financing a stellar arc is less a transaction and more a metamorphosis of human ambition. It requires us to value time in centuries, to invest in outcomes we will never witness, and to place a bet on the enduring curiosity and cooperation of those who come after us. The ledger for such a project cannot be measured only in currency, but in commitment, in patience, and in a shared story that stretches from our present moment to a point of light in the distant dark. It asks what we are willing to sow today for a harvest that will feed souls we will never know. This economic and philosophical leap may be the final, and most human, test we must pass before the engines can ever light. For if we can align our fleeting economies with the timeless rhythm of the cosmos, we will have proven ourselves ready not just to build a ship, but to inherit the journey. The final test of a stellar engine will not be written on a blueprint, but etched into the unforgiving vacuum between worlds. Long before a ship points its prow toward Proxima Centauri, its heart must first learn to beat in the backyard of our own sun. The inner solar system, from the dusty plains of the Moon to the swirling storms of Jupiter, will become our essential proving ground, a cosmic workshop where we graduate from theory to relentless practical reality. This is where the dream of centuries-long power endures its first, brutal exams, not in the abstract but in the service of more immediate ambitions. Consider the next generation of lunar outposts, envisioned not as fleeting flags but as permanent settlements. They will need power through the 2-week lunar night, a deep cold where solar panels are useless. Or picture the sprawling industrial complexes of future asteroid miners, where robotic refineries must operate for years, processing rock into fuel and building materials far from any power grid. These are not interstellar missions, but they demand the same core technologies: robust, autonomous, and unimaginably durable energy systems. The first steps are already being taken. Projects like NASA Kilopower are pioneering compact fission reactors, scaled to fit on a lander, capable of generating steady, reliable electricity for a decade or more without refueling. These small, rugged units are the foundational lessons. They will teach us how to harden electronics against the relentless hail of cosmic radiation that floods space, how to manage waste heat through radiators that must function perfectly for years without maintenance, and how to design control systems that can operate autonomously, making millions of tiny adjustments without a single command from Earth. Each successful mission powered by such a reactor is a data point, a hard-won answer to 1,000 practical questions about material fatigue, thermal cycling, and reliability in an environment that forgives no error. But fission is only the primer, the true intermediate exam. The mission that would signal our readiness for the interstellar leap would be a journey to the king of planets. A probe sent to orbit Jupiter or to dive into the atmospheres of its icy moons faces a profound energy challenge. At that distance, sunlight is a mere 25th as strong as it is at Earth. Solar panels become vast, fragile, and inefficient. This is the perfect environment to debut the next generation, a compact fusion reactor. Imagine a spacecraft not much larger than those we send today, but powered by a contained miniature star. It could operate powerful radars to map the hidden oceans of Europa, run intense heaters to bore through miles of ice, or support a fleet of drones in the thick Jovian atmosphere, all on a fuel load measured in kilograms. A successful Jupiter mission powered by sustained fusion would be the definitive proof of concept. It would demonstrate that we can not only create a star in a bottle, but that we can package it, launch it across 500 million miles of space, and command it to run flawlessly in the most demanding environment this side of the interstellar void. It would prove that our power systems can thrive in the deep cold and darkness, far from the nurturing light of our sun. This is the critical bridge. The technologies validated around Jupiter, the radiation-hardened superconductors, the autonomous plasma control, the gigawatt-scale heat management, are the very same technologies scaled up to become the engine room of a starship. The inner solar system is our training ground, where we learn to walk so that one day we may sprint between the stars. Each circuit completed around the Moon, each asteroid processed, each data packet received from a fusion-powered probe at Jupiter, is a stitch in the immense, patient tapestry of our departure. It turns the grand vision from a single, impossible leap into a sequence of logical, achievable steps, each one building the confidence and the capability for the next. And as we master power in the realm of our sun, we must then confront the ultimate destination, not as a distant point of light, but as a real place with its own challenges and gifts. The universe has already built the engines we dream of. Before we sketch a single blueprint for a starship's heart, we can look up and see the principles in action, written across the cosmos in light and gravity. Nature operates particle accelerators of unimaginable power and maintains fusion reactors that burn steadily for billions of years. Our most ambitious designs are not inventions, but imitations, attempts to replicate the universe's own flawless engineering. Consider the humble pulsar, the spinning core of a dead star. Its intense magnetic field, trillions of times stronger than Earth's, rips charged particles from its surface and whips them into space at nearly the speed of light. This creates a lighthouse beam of radiation and a torrent of high-energy particles, a natural particle accelerator of staggering efficiency. It is a cosmic dynamo, converting rotational energy into electromagnetic fury, demonstrating a form of power generation we are only beginning to comprehend. Or look to the awesome spectacle of a black hole's accretion disk. As matter spirals inward, drawn by irresistible gravity, it is heated to millions of degrees by friction and magnetic forces, glowing brighter than entire galaxies. This process converts gravitational potential into radiant energy with an efficiency far beyond any chemical or nuclear reaction we can achieve on Earth. These are not mere curiosities, they are proof of concept demonstrations on a galactic scale. They show that the universe routinely manages energies that dwarf our entire civilization's output, and it does so with an elegance born of fundamental physics. Some researchers, contemplating the search for intelligent life, have even proposed that an advanced civilization might not build Dyson spheres at all, but might learn to tap these ready-made cosmic power plants, using the gravity of a black hole or the magnetic fury of a pulsar as their ultimate battery. For our own more nascent efforts, the lessons are immediate and profound. A star like our Sun is the ultimate model of a stable fusion reactor. For over 4.5 billion years, it has maintained a perfect balance between the outward pressure of its radiant energy and the inward crush of its own gravity. This equilibrium is a masterclass in feedback control, a system that self-regulates with exquisite precision across timescales we cannot yet fathom for our own machines. Our challenge is to replicate that stability not in a body of gas millions of miles across, but within a magnetic bottle a few meters wide. By studying the subtle dances of plasma in stellar cores and the magnetic geometries around neutron stars, we learn the rules of managing stellar fire. The cosmos is not just our destination, it is our greatest teacher. The principles of energy conversion, storage, and management that we must master for a 1,000-year voyage are not human concepts. They are universal laws already expressed in the silent, enduring machinery of the heavens. Our task is to learn their language, to read the instructions that have been glowing in the dark since the beginning of time, and with care, to write them into the heart of our own ships. This seamless orchestration of power points toward a profound truth. The ultimate energy system for a 1,000-year voyage will not be a single, miraculous engine hanging in the ship's stern. It will be something far more elegant, a deeply integrated hierarchy, a symphony of technologies where each instrument plays its part at the perfect moment. Think of it as a living energy web, an intelligent circulatory system for a vessel that is itself a world. At its heart might thrum a primary reactor, perhaps an antimatter-catalyzed fusion core, reserved for the immense power demands of major course corrections or the initial decades-long acceleration burn. This is the ship's powerhouse, its muscular heart capable of roaring to life when needed. Yet, for the long cruise between maneuvers or for the delicate act of arrival, a different system takes over. Vast, gossamer thin photovoltaic skin could coat sections of the hull, drinking in the faint starlight to power the ship's quiet, background hum, the life support, the sensors, the constant computations. For sudden, peak energy demands, like firing a powerful laser communication array or adjusting a massive magnetic sail, banks of quantum battery buffers would activate, absorbing and releasing colossal surges in an instant. And for braking at the destination, that magnificent magnetic sail would unfurl, using the stellar wind of the new sun to slow the ship without spending a single drop of precious onboard fuel. This energy web does far more than just push the ship forward. It powers everything. It would feed the delicate, humming warp field generators if such a technology ever moves from equation to reality, gently bending space-time around the hull. That same relentless current would energize the quantum computers that serve as the ship's navigational mind, calculating position by tracking the precise spin of distant pulsars, the universe's own lighthouse network. It would maintain the artificial gravity plating underfoot, cycle the air and water, and power the nanite swarms that mend microscopic cracks in the hull. Every system, from the most profound to the most mundane, draws from this unified, intelligent grid. This represents the absolute apex of systems engineering. It is no longer about building a better generator or a more efficient battery in isolation. It is about weaving them into a seamless, intelligent whole where power generation, storage, management, and utilization are indistinguishable facets of a single conscious entity, the ship itself. The energy system becomes the ship's metabolism, its nervous system, and its soul all at once. This holistic view is the crucial, final insight. The breakthrough that enables a centuries-long Starship will not arrive as a single, headline-grabbing invention. It will not be the sudden discovery of a warp drive or a perfectly efficient antimatter bottle alone. The true enabler will be the masterful, patient integration of many breakthroughs, each solving a piece of the puzzle, and all designed from the start to work in flawless, silent concert for 1,000 years. It is the art of making the extraordinary seem effortless, of building a machine so complex that it appears from the inside as simple and reliable as sunrise. The vessel that finally leaves our solar system will carry with it the totality of our understanding, not as a collection of parts, but as a unified testament to a civilization that learned to think in circuits of energy, time, and life, all woven into one enduring thread. This tapestry of ambition reveals a profound truth about our place in the cosmos. We have traced a line from the chemical fires that first warmed our ancestors to the theoretical manipulation of space-time itself, all in service of a single, luminous goal: to build a vessel that can carry life across the ocean of night. The fusion torch, the antimatter spark, the magnetic sail catching stellar winds, these are more than mere machines. They are physical manifestations of a question: what happens when a species decides its story should not end with the sunset of its home star? Each concept, from the nearly attainable to the wildly speculative, represents a different answer, a different philosophy of journey. One says we must carry our fire with us, forged into ever more perfect forms. Another suggests we must learn to gather sustenance from the thin breath of the galaxy itself. They are all declarations written in mathematics and metal that we choose to look outward. The monumental scale of these challenges is not a barrier but a beacon. It forces innovation in materials science, in artificial intelligence, in closed-loop biology, and in our very social structures. The Starship engine is not a destination, it is a catalyst for the evolution of an entire civilization. It demands we think in centuries, cooperate across generations, and value patience and precision as highly as power and speed. While we may never see a black hole drive or a warp bubble grace the skies of Earth, the relentless pursuit of these ideas illuminates our path. It teaches us about the fundamental nature of energy and reality, and it pushes our technology toward greater resilience and intelligence right here, right now. The ultimate engine, when it is finally built, will be the sum of all these struggles and breakthroughs. It will be a testament to a species that learned to harmonize the roar of a contained star with the silent, enduring will to see what lies beyond the next horizon. That journey begins not in a shipyard but in our collective imagination. Which of these celestial hearts speaks to your vision of the future? Is it the elegant promise of fusion or the raw potential of matter itself? Share your thoughts below and join us as we continue to map the frontiers of what comes next.